In this problem, we're assuming that G is a cyclic group. So it's got a generator. And we're also assuming G has exactly 3 subgroups. The entire subgroup G itself, any group is a subgroup of itself. A non-proper subgroup, we say H is a proper subgroup of G if H is a subgroup that doesn't equal all of G, but here that does equal all of G. That's a non-proper subgroup. The trivial subgroup containing just one element, that's always a subgroup of any group. One element, that's the identity element in the given group, will always be a subgroup of that group. It's called the trivial subgroup. And one other one, H, whose order equals P, where P is prime. The goal is to prove that the order of G is P squared. Wanted you to think about this ahead of time using a theorem. I hope you've at least figured out that the key theorem to use is the fundamental theorem of cyclic groups. Okay, at least if you had an inkling that that was the best thing to use, that's definitely progress. What does it say? It says every subgroup of a cyclic group is cyclic. So we have a cyclic group here. So yes, G itself is cyclic. Trivial subgroup is always cyclic. It's generated by itself. And the H, we're assuming has order P, is also cyclic. Moreover, if the order of a given cyclic group, think of that as an arbitrary cyclic group right there, is N. That's an arbitrary finite cyclic group there, just notation for the generator. Then the order of any subgroup of that cyclic group is a divisor of N. Got a subgroup of a cyclic group. The order of the subgroup has to divide the order of the bigger group, the order of the bigger cyclic group. And even more, for each positive divisor K of N, the group, the original cyclic group, has exactly one subgroup of order K. And you can even specify what it is with this notation. Exactly one. So that's really, really saying a lot here. So how do we apply this now? You could try to argue by contradiction. See if we can write down the idea of the proof. Certainly, G has to have order bigger than P. P is prime. The only divisors of the prime P would be 1 and P itself. If G had order P, it would have only 2 subgroups for the divisors of P, 1 and P. Trivial subgroup and the non-proper subgroup, G itself. So certainly, the order of G is bigger than P. Moreover, since the order of H equals P, P has to divide the order of G, right? Because cyclic groups, for each divisor of the order of the cyclic group, you're going to have a subgroup of that order. And also if you have a subgroup of that order, it's going to divide the order of the cyclic group. H has order P. P has to divide the order of G. This is a divide symbol, and here's an order symbol. By the way, the fact that we're using these lots of vertical lines here is another reason why some people use O for order instead of like absolute value signs. But this is what our book uses for order. You don't need to write that. I'm just making a comment there. So the possibilities would be that the order of G is a power of P, or a power of P times some other primes. You have I hope intuitively, if you have really high powers of P or lots of other primes in the prime factorization of the order of G, that there'd be probably lots of subgroups of G, which would contradict the fact that we're assuming there's only 3. Yeah, like, okay, so let's not do a full argument here, but for example, if if the order of G were, say, P cubed. So I'm kind of arguing by contradiction right now. But I'm not really doing the actual proof because I'm just sort of problem solving here. If the order of G were P cubed, how many subgroups would G have? G is still cyclic. By that fundamental theorem of cyclic groups, it would have exactly one subgroup for each divisor of P cubed. How many divisors of P cubed are there? 1, P squared, and P cubed. 4. G would have 4 subgroups of order 1, P squared, and P cubed. This is by the fundamental theorem of cyclic groups, FTCG. And you could give the same kind of argument if G had order P to the 4th, P to the 5th. G had order P to the 5th, there'd be 6 subgroups of orders 1, P squared, P cubed, P to the 4th, and P to the 5th. In general, you could give a full proof saying if G had order P to the K, where K is greater than or equal to 3, you're going to have more than 3 subgroups. On the other hand, if the order of G is, say, P squared times Q, well, or just P times Q, where Q is another prime distinct from P, so you've got a prime factorization as a product of 2 distinct primes. Once again, the fundamental theorem of cyclic groups would apply to say you're going to have how many subgroups? Think about it a little bit. You'd have to have 4 of them. Order 1, order P, order Q, and order P times Q. 1 subgroup for each order that divides the order of the group. G would have, once again, 4 subgroups of order, this time 1, P times Q, and, well, I meant to say Q there, Q and P times Q. The dash is here referring to writing the same things that I wrote up there. Once again, that's the fundamental theorem of cyclic groups. What if the order of G was even bigger? What if the order of G was P times R, or P to the K times R, where K is bigger than 1, say, and R doesn't have any prime factors involving P, but could have a bunch of other prime factors, even bigger. Okay, you're going to have even more subgroups. How could you say that in a nice way? Actually, what you could do to make things simpler on yourself in this kind of context is you could say G would have a subgroup of order, for example, P squared, or P times Q, where Q is some other prime factor of R, and use the same argument as here and still get a contradiction. That subgroup would have 4 subgroups itself of these orders or these orders, depending on how you gave the argument. No matter how you do it, you're going to get a contradiction to the fact that you only have exactly 3 subgroups. I could see this kind of problem coming up with the test, not as a proof, but as maybe a calculation type of question, or a true-false type of question, or something like that, or a fill-in-the-blank kind of question. Something like, if you got a cyclic group G of order P squared, how many, or sort of turn it around. If G was cyclic with order P squared, how many subgroups would it have? Or if it had order P cubed, how many subgroups would it have? Or maybe I'd pick particular numbers. Maybe I'd say G has order 2 cubed times 3, 8 times 3, 24. How many subgroups does it have? How many subgroups does a cyclic group of order 24 have?